Hello everybody, welcome back. So this is a course on an introduction to statistics for the psychological sciences. I'm your professor, Rob, and today we're going to be going over the third part of a four-part lecture series. In the first two parts, we covered frequency distributions, the distinctions between grouped and ungrouped frequency distributions, how to construct them and how to interpret them. And that was the material that was presented in the third chapter of your textbook. Today, we're going to be going into the material from the fourth chapter, which basically describes common ways that people describe a distribution of data, right? And so to do this, we need a measure of like the middle, the center point around which the data fall. These are known as measures of central tendency. And then we also need to know how spread out the data is, how dispersed it is. And this is going to be the content of the next fourth part of this lecture, which is measures of variability or dispersion. And so I did want to just quickly bring to your attention that, we're going to continue doing these lectures. As always, you're going to find the PowerPoint slides over here. But as we move forward up here, you're going to find a virtual whiteboard. And we will eventually, once we get into doing some more robust hand calculations, we will be doing problems by hand. And so I'll kind of fade in and out here, and we'll work on problems together. I don't think it's going to be necessary during this presentation, as we're just really kind of touching in on some key conceptual aspects of statistics. Once we get to working actual inferential statistics, we will be doing them together. So I just wanted to bring that to your attention. But for now, why don't we jump into the content and describe measures of central tendency? Okay, so what is central tendency? Well, it's kind of what it sounds like. It's a measure that identifies the location where the center point is on a distribution of data. So central tendency allows us, the goal is to try to find the single best score to represent the distribution. Now, there are three primary measures of central tendency: the mean, the median, and the mode. And there isn't one that's necessarily best, so to say. It really depends. It depends on the type of data that you're presented with and the shape of the distribution of the data that's going to determine which is the most appropriate measure of central tendency. But let's just start with the most common shape of a distribution, which is the standard normal distribution. So it looks like this. You can see here we've got a distribution of letter grades, right? So we've got the tails have an F and an A, and then going towards the middle we have D's and B's, and in the middle we have a C. Now what that y-axis is measuring on this scale is frequency. The frequency of occurrence of a given value. And so you can see here that there were more people who had C's than people who had F's or D's or B's or A's. Now, one property of the normal distribution, and we will be going into many more details about this next week, is that a normal distribution is symmetrical. You can fold it in half, it's a mirror image of itself. Right? But if you were asked, just looking at this, like say I were asking you to predict a student's score on the exam, and you had no other information about this student. You didn't know anything about them, right? Just out of thin air, if you were trying to predict what they scored on the test, what would your best guess be? Well, in this case, your best guess would be a C, because it's the most frequently occurring score, right? And this is a property of the mean. When we're dealing with the normal distribution, of scores, the mean is typically our best guess in the absence of other information, right? And keep in mind that when we're dealing with statistics, most of the time, particularly inferential statistics, we're in the business of guessing or of predicting. We're trying to predict how people are going to do. We're trying to predict who's going to get depression, who's not going to get depression, who's going to be happy, who's not going to be happy, and try to explain why people are different in that. So if we want to make a prediction in the absence of any additional information, our best guess is going to be the mean. But there are situations when the mean would not be our best guess. Sometimes it may be more accurate to describe the center point of a distribution using the median. And other times it might be more appropriate to use the mode to describe it. So what we're going to do in this lecture is go through and describe the differences in these measures of central tendency, talk about some of the key properties of them, learn what they can reveal to us about the underlying shape of a distribution, and finally try to come to some kind of rules of thumb about the conditions under which it's most appropriate to use one measure of central tendency over another. So we'll start with the most common, the mean, right? Everyone's familiar with the mean. We computed means in the last section when we were talking about summation notation. And essentially all the mean is the sum of all of the scores divided by the total number of scores. In other words, it is the sum of all x values divided by n. Now, I want to bring your attention to these two formulas that are on the screen. So the first one, we have mu. Mu is equal to the sum of all the scores divided by the total number of scores. And for the sample mean, the x bar, the only difference is what the symbol is, right? What we're calling it. Computing a mean is going to be the same for a population as it is for a sample. There is no mathematical difference, right? But it is important to recognize that the population mean, it represents something conceptually different from a sample mean, even though the underlying math behind it is the same. So if we looked at these scores on how many hours of sleep a person received the night before, we can compute the mean by adding up all the scores and dividing by the total number of scores. And we would get a mean of 7. So one interesting property about the mean is it kind of serves as a balance point. So if we look at this slide here, we can see that 6 is 1 away from 7, and there are 2 of them. Right, so the difference between 6 and 7 is 1. There's 2 of them, so we've got 2. And then the difference of 3 from 7 is 3, 4, 5, 6, 7 is 4. So that's kind of like a total of 6 difference points away from the middle. Now, if we look at the right side of the distribution, we have 1, 9, which is 1, 2 away. And then we've got 1, 11, 1, 2, 3, 4. So that's 6 as well. The mean balances the differences from the mean on each side and makes them equal. So this is an interesting property of the mean. The mean is sensitive to the exact value of all scores in a distribution. So if we have an extreme score that's way, way, way high or way, way, way low, this is going to skew the shape of the distribution, and the mean is still going to try to balance it out, and it might not be the best measure of central tendency. So, for example, here we have that balanced distribution we were looking at before, but if we take the 11 away, it's going to be off balance. And the only way we can balance it again is to move the mean towards that shorter or the left-sided end. So let me try to provide another way to explain this, right? So say you were an employee and you're working for Tesla, and we plot out the distribution of employee annual salaries at Tesla. So we have this balance point here. You can see at $70,000 a year. Pretty good salary, right? So what would your best guess, if you had no knowledge of who they were, if you just had to try to predict what some random person who worked at Tesla made, you would likely predict 70,000. Now, what would happen if Elon Musk was in that pool and we just tried to use the mean? You know, most people are making around 70,000 a year, but Elon Musk, he makes 2.3 billion a year, right? So he is going to really dramatically influence what that mean is. But the mean is still going to balance out so that the deviations are equal above and below that point. So another way of kind of saying this is that the sum of the deviations about the mean equals 0, right? So the deviation is simply the distance from a raw score to the mean of the distribution. So in other words, the differences below and the differences above the mean cancel out. If we wanted to try to see, like to measure that deviation, we could do something like square the differences. And we will discuss this as when we go into measures of variability. This is a property of standard deviation. But so the mean minimizes the sum of the squared deviations about the mean. So this is a property that makes the mean very useful for statistical procedures, because oftentimes, it's very common for statisticians to use procedures that attempt to minimize the squared deviation of some kind of prediction, right? So if we know the distribution of Tesla salaries and I'm trying to predict it, my prediction is probably going to be slightly off from what reality is. But we can use this property of the mean that minimizes the sum of the squared deviations as a way to figure out which model is most appropriate. Okay, so again, the key features of the mean are that the sum of the deviations about the mean equals 0, right? So that is essentially the definition of the mean, is that the differences below and the differences above cancel each other out. And if we square them, if we square those differences, the mean is the point at which the sum of the squared deviations is smallest. Okay, so let's look at some other data here. Let's look at sleep data, and I'm going to try to explain this deviation thing, minimizing deviations with some more graphics. So let's take, for example, sleep data. We already discussed this. This is now in frequency table form. So we add up all of these values. We've got one person with 11, one person with 9, 2 people with 6, and 1 person with 3. So there's still 5 people in this distribution. They sum up to 35. We divide by n, and we get a mean of 7. So now here's a graphic of their values plotted, right? So we have their sleep in hours and their ID on the x-axis. Now, if we draw a line for the mean, we can see some of them are above the line and some of them are below. Now, say you had to predict, in the absence of any information, how many hours a night of sleep the average person got. Well, the mean would be your best guess. But no one slept for a value of 7 hours, right? So no one slept for 7 hours. They slept for 9, 11, 3. No one slept for 7 hours. So there's an error in the prediction. However, we can see that, our prediction of the person with 9 is kind of 2 units off, right? And this is the deviation. How much our prediction is different from what happened in reality. So the pink and the orange lines are the distances or deviations for each value from the mean. So we add these deviations together and they're going to equal 0. So for example, we've got a deviation of 2, -4, -4, -1, and -1. Those add up to 0, right? So the mean minimizes the sum of the squared deviations. And so this is why the mean is going to be our best guess in the absence of other information. So notice that the sum of the deviations in that picture equaled 0, and the sum of the squared deviations was smallest at the mean. So now let's talk about our second measure of central tendency, which is the median. So the median is basically the midpoint in a distribution of scores whenever they've been listed in ascending order, smallest to largest. So a value, so the median represents the value below which 50% of all people fall in the distribution. Now, because we're just looking at the position, we're looking at we're ordering them from smallest to highest and looking at the midpoint, it doesn't really matter what the values of any of the individual people are, right? So the median in this way is going to be much less sensitive to extreme scores or outliers, right? So think about what would Elon Musk, if Elon Musk was in the room and we're trying to predict salary, how would he influence the median? Well, he wouldn't. He'd just be another person, another person in the list. But his value and the magnitude of his salary would not bias our estimate of the midpoint. So how do we do this? Well, to locate the median, we have slightly different method whenever we're dealing with odd numbers of participants and even numbers of participants. But basically what you do is you sort them from smallest to largest, and then you identify the middle score. And so in this case, the middle score is going to be 6. That is the median. Now, if you had 10,000 scores, you probably wouldn't want to spend your weekend ordering them and counting them up. So to locate the median in a large distribution, you basically take n plus 1 and then divide it by 2. And at that position, that is going to be the median value. So what about if we have an even number of values? Well, if there's an even one, there's not going to be a 1 score at the midpoint. So what we do is same thing as before. We put them in ascending order, and then we take the average of the centermost pair, right? So one's going to be, there's going to be 2 values that are the middle. And so basically, we line them up. 6 and 9 are the midpoints. You can see we have 2 below and 2 above. And we divide by 2. So we have a median of 7.5 for this data. Now, if you're trying to locate the median in a large distribution, you basically just average the values in the n divided by 2 and n divided by 2 plus 1 positions. Now, another interesting thing about the median and the mean, when combined, if we have both pieces of data, it can tell us a little bit about the underlying shape of a distribution. So here we have our example with Tesla employee salaries. Elon Musk's in the room. His salary's counted, and he's just really skewing this distribution, right? He's pulling the tail towards the positive end, right? And this is called a positive skew. Now, what's going to happen here is our estimate of the mean is going to be really warped by his presence, right? He's going to pull that mean way out. And so you got to ask yourself, I mean, if the mean at this point is $100 million a year, is that an accurate representation of the distribution of employee annual salary? No, it's not. I mean, he's dramatically inflating the average salary of Tesla employees. So the median, on the other hand, is not going to take his actual salary value into account. It's just going to take advantage of, it's an ordinal measure, right? It's going to take the value of position in that ordered distribution. So, I mean, it wouldn't make any difference to the median if Elon Musk made $111,000 a year or $50 billion a year. He's just one position. And so for this reason, the median might be a much more representative estimate of this distribution of data. And so when we look at, if we calculate the mean and the median of a distribution of data, this is an interesting property. The mean, if we have a positively skewed distribution like we have here, the mean will be higher than the median. And if it's negatively skewed, the mean will be lower than the median. And if it's normal, the mean and the median will be approximately equal, right? So it's not just that these values are effective at describing the center point, but how they are related to each other can give us some insight into the underlying shape of the actual distribution that we're working with. So the third type measure of central tendency is the mode, right? Now the mode is the most frequently occurring score in a distribution. So for example, going back to our sleep data, the value of 6 hours occurred twice, and that was the most frequent value. So that is the mode. Here's another example. So we've got this distribution of just random data. The mode is going to be 32 here because it occurs 3 times. So where's the mode here? Well, I'm sure you found it. The mode is 5. It's the highest peak on a histogram or in the normal distribution, right? So the mode is going to follow that peak around no matter how skewed it is. Okay. Now, sometimes we can have bimodal distributions, right? Where just the way the data is set up or the nature of the variable, where there are 2 values that are equally frequent. So here an example of this would be if we looked at test scores among students who did study and who didn't study. So there might be an equal number of people who failed as who got an A on the test. So this is an example of a bimodal distribution. Now, typically, if you're going to use mode is very helpful when you're dealing with nominal variables. It describes, the most frequent eye color, for example, which is going to be brown in this distribution of data. So if you were looking at a variable like ethnicity, right, a nominal, which is a nominal variable as well, the mode is going to be a good place to start to describe the distribution of nominal data. Okay, so here we go again with this property of how the mean, median, and mode are related and how we can leverage their values to determine the underlying shape of a distribution. So for a negative skew, you're going to have the mean as the lowest, then the median, then the mode. For a positive skew, the mean is going to get pulled out towards the direction of skew. The median is going to be next highest, and then the mode last, right? In a normal distribution, which is what we really want to be working with most of the time, at least in parametric statistics, is the mean, median, and mode should all be equal. Okay, so here is an example of how these are related when we're dealing with different types of symmetrical distributions. So we have the normal distribution on the left, but we can also have an entirely symmetrical bimodal distribution. If we had a bimodal distribution, then we're going to have the mean and median being equal, and we're going to have the two modes on either side of it. And then, of course, there's an example where all values are equal, and then the mean and median are going to be equal, but there isn't going to be a mode. So which one should you choose to use to describe the central tendency of a data set? Well, most of the time you're going to use the mean, but the mean is only effective to the degree that your distribution is normal. Sometimes your data is not going to be normally distributed, and when that's the case, it's not going to be advisable to use the mean. If the distribution is highly skewed, right, meaning, so skewness is a deviation from symmetry, where one tail is pulled out in the direction of some outlier, right? And if, so it's not a mirror image of itself. If the distribution is skewed, then it's going to be more likely that the median is the best estimate of the center point, because the median is not as sensitive to those extreme values. However, the mode, you'll probably use the mode when you're dealing with qualitative data, particularly nominal variables. So if you were assessing ethnicity, most accurate way is the mode. So that wraps up this lecture on measures of central tendency. I hope you found it helpful. If you did, please don't forget to like the video and subscribe and hit the notification bell so you'll get advance information the second I post lecture content. And I look forward to working with you through the next portion of this lecture, which are measures of dispersion or variability. Okay, well, thank you. Have a good day.